I'm Christopher Jefferson from the University of St Andrews, and I'm here to talk about applying constraint programming to group theory. A bit of background and some motivation for this talk. So I did my PhD at the University of York in representations in constraint programming, and during my PhD and afterwards, I was involved in writing the constraint solver Minion. I was the lead author of the original version, although many people have contributed since. What was interesting about Minion to me is it was a constraint solver which supported multiple ways of implementing variables. We were not unique in this. At the same time, there were other solvers investigating the same idea, in particular G-code. At that point, I was asked by Steve Linton, a professor at St Andrews, to look at this partition backtracking paper. He was trying to understand this paper. He was finding it extremely difficult to read. It was a 20-year-old maths paper, and the algorithms it described were in use in all group theory systems, but no one was really finding it easy to understand, generalize, extend the algorithms. And he said, it looks a bit like CP. So here's this paper, and it is permutation group algorithms based on partitions, a technique for computing in permutation groups of high degree. This technique uses the idea of ordered partitions. I'm going to get more into this. Introduced by Brendan McKay. Those of you who have come across the naughty system for graph isomorphism, this is what's being discussed. So I'm going to start by telling you a bit about what group theory is and why we might care. And then I'm going to talk about what this paper did, how it is interesting, I think, to CP people. Even though it was written in 1990, it does things that CP solvers aren't good at. On the other hand, there are things CP solvers do that this paper wasn't good at. You would hope our entire field had features this paper didn't provide. And how I worked with some people to combine the two and produce a new system for solving group theory. So, to begin, what is group theory? At a fundamental level, the idea behind a group is in any situation where you have a set of operations. So in the case of a Rubik's Cube, the rotations of the Rubik's Cube. And what you need is, you need that if you apply two of the moves one after the other, it makes sense. Like you get another move, and moves have to be invertible. So with a Rubik's Cube, we can twist it twice, we can twist it back to where we started. So a very common place for groups to come up is in symmetries. So here's a hexagon, and a hexagon has 12 symmetries. There's 6 reflections represented by the lines. There are the rotations of the hexagon, and you can rotate and reflect the hexagon, and it turns out that is the same as a reflection. A very common type of symmetry which occurs all the time in constraint programming is having equivalent objects. So if you're scheduling trains, there's a good chance that a train carriage is a train carriage. And you don't want to consider all of the different schedules where all the train carriages are permuted. And there is a huge number of papers on this topic. I have been involved in a very small number of them. I am not in this talk going to go into details of how you can handle symmetries in CP. That is a really interesting topic. It would be an entire hour tutorial by itself. So that's not what I'm going to do here. So let's get a formal definition of a group. So we have our finite set G. These are the things in the group. So in the case of the trains, this is swapping some trains around. In the hexagon, this is the reflections and rotations. In the Rubik's Cube, this is a sequence of 0, 1 or more twists. We need that if we do one of the things in our group followed by a second thing, we get another thing in our group. We need the group to be associative. So if you do S and then T, and then you apply U to it, you get the same thing as doing T then U and then doing S before. This is the type of property that tends to almost always be true, but we need it for our thing to be a group. If the group is finite, that's all we need. There's a couple more things we need if the group is infinite. And also these are useful things to know. If the group is finite, you can prove these things. There will be an identity element. So this is like the thing that does nothing. So in the case of trains, this would be don't move any trains. In the case of the hexagon, this is don't reflect or rotate, just do nothing. In the case of the Rubik's Cube, once again, this is do nothing. Also, every element will have an inverse. So each reflection we can unreflect. In the case of rotations, we can rotate back. In the case of the Rubik's Cube, we can rotate and rotate back. So we have these. So we can check each of these rules applies to our basic things. But groups are extremely abstract in that general formulation, and it's very hard to operate them in a computer. So we tend to consider what are called permutation groups in many practical applications. And in particular, all the groups that come up in constraint programming tend to be permutation groups. The idea of the permutation group is looking at these groups. We don't tend to think of them as acting in a very abstract way. So in particular with the trains, we don't just think of the operations as abstract things. We think about the set of trains and how the trains are affected. In the case of the Rubik's Cube, we can consider each of the coloured squares, and we can consider how each rotation affects the location of the coloured squares. In the case of the hexagon, we can consider the 6 corners and just consider what each of the moves do to the 6 corners. And if you know where the 6 corners go, you know everything that's happened with the hexagon. So we in this talk are going to just consider permutation groups. And permutation groups now, G is still going to be our group. Now we have a finite set T. This is the thing on which the group is acting. And now our group is a set of bijective functions, so things that map T to T. So the trains, or the corners of the hexagon, or the squares on the Rubik's Cube. So we still need, when we apply one function and then another function, we get another member of the group. There, we need the group to contain the identity function, the bijective function that does nothing. We need the inverse to be in the group. If we have a function, we have to have its inverse. So let's have a concrete example. So here's a hexagon on the left. This is like the standard labeling. And then on the right, I have done the reflection straight down the middle. So you can see the top 2 points have swapped, 3 and 6 have swapped, and 4 and 5 have swapped. And at the bottom, I've given this in what is called cycle notation. This is the standard way people write groups. And the idea is in each bracket, we give a sequence of points and where they are moved to. So this should be read as like, where there was 1, there is now 2, and 2 has moved to where 1 is, 3's moved to where 6 is, 4's moved to where 5 is, 5 moves to where 4 is. Because these cycles are only size 2, like it's not super clear what's going on, so let's consider a longer cycle. Here I've done a rotation. So you'll see that 1 has moved forward 1 space and everything's moved forward 1 space. And this is written in cycle notation at the bottom, and the way to think of this is, so if you look at the left, where 1 was, there's now a 6. Where 6 was, there's now a 5. Where 5 was, there's now a 4. 4 was 3. Where 3 was, there's a 2. And where 2 is, we go back to the start of the cycle. That's where 1 is. When we write cycles, we typically don't bother writing the things that don't move. So you could write open bracket 2, close bracket to represent 2 doesn't move, but we generally don't. So we rarely find all the members of a group unless the group is small. Now, there's different definitions of small, but groups that mathematicians would consider not very big can have, say, 40 factorial members. So a number we're never going to enumerate. In group theory, we might enumerate a group up to like 1 million members, but we typically don't want to do bigger than that. But because we know that groups are closed, by which I closed under composition and inverse, so if I give you some members of the group, you can keep composing them and inverting them. We don't have to give you all of the group. So for the hexagon, if I just give you one of the reflections and one of the rotations, then I can generate all 12 symmetries of a hexagon. And so I can say the symmetries of a hexagon are you rotate once, you reflect once, and then you do everything else. And many, many algorithms in group theory act on sets of generators and produce sets of generators because we just couldn't enumerate the whole group. So, what kind of problems do we traditionally solve in CP with permutation groups? So the classic problems that people have solved in the past is when a problem has a symmetry group. So we might want to know, given 2 solutions, are they symmetric? Because a user might not want to see 2 solutions which are fundamentally the same under, say, swappings of trains. Are 2 partial assignments symmetric? So say we've half filled in the variables. Are they symmetric? Because if they are, we don't want to search both of those 2 partial solutions, and this is the fundamental idea behind symmetry breaking techniques, dynamic symmetry breaking techniques like SBDD and SBDS and many others? Or is the solution somehow as small as it could be under some ordering under a symmetry group? So is there a way I can permute a partial solution to make it smaller? This is, very briefly, and I will admit slightly confusingly, the idea behind static symmetry breaking techniques, the most famous of which is putting lexicographic ordering constraints on. Once again, a fascinating topic I could spend an hour talking about, but not this talk. What do other people want to do when they have some groups? In particular, mathematicians consider groups all the time. They might, given two groups, want to find their intersection. Turns out this is not a trivial problem. Remember, I'm giving you the generators of two groups and asking you to find generators for the intersection. Groups themselves can have a symmetry group. This is called the normalizer. Or we might want to say, given a group and a set or a graph or a matrix, what members of the group map this set or graph or matrix to itself? I'm just going to briefly mention another important class of problems is what's called coset problems. So here we have a group and a permutation. I'm considering permutation groups here. Then basically multiplying a group by a permutation is a coset. So you can think of it as a group where we've just shifted every element of it by some permutation. Cosets come up when we want to map some object to a second object. So if I want to know all permutations that map one graph to a second graph, this will be a coset. You don't need to worry too much about cosets. I just wanted to mention it because the word comes up a lot. So let's imagine we wanted to solve this using constraint programming. So how would we implement constraints on groups? So you can imagine the first idea would be, well, how do we represent a group using finite integer variables? And then we'd go away and we'd write a propagator for A intersect B equals C, and a propagator for A is a subset of B, and all these different things. And we'd write a paper for each of these probably, and this would be great. We did this with semigroups. So myself, Tom Kelsey, Laz Kotoff, and Andreas Dissler did this. We did this for semigroups. A semigroup is just a group where you don't have inverses. And we wanted to find all semigroups with some particular properties of some given size. So we represented the semigroup as a matrix. We added constraints to make that matrix be a semigroup, and then we counted all the solutions. So for example, one thing we did was look for all the semigroups of order 10. And basically, Andreas Dissler did a bunch of work where he managed to prove mathematically, he managed to count most of the semigroups. That's the bottom number. I'm not going to even attempt to read that number out. And then the bit where he couldn't do it mathematically, we did it with a constraint solver. We did it with Minion. Minion found 222 billion semigroups. Took about 60 CPU years. We counted them all, and also we counted, while we were doing this, the number of certain subclasses. And this was the first time these had all been enumerated. And so great. So we did this. What's the problem? The problem is this doesn't scale. So here, these semigroups are of size 10. This isn't a semigroup or group that permutes 10 things. This is just the group has 10 elements. That's it. And this just doesn't scale to larger sizes. We couldn't scale this much beyond this size. The problem is we're not storing the generators. So what if we represented the group as a list of generators? And you can imagine how you do this in constraints. Each generator is a permutation. We're doing a permutation group. So we have a list of permutations. A permutation's just n numbers from 1 to n. As far as I can tell, this doesn't work. There will be many solutions for the same group because there's many, many generating sets. And even if we ignored that, how would we propagate A intersect B equals C for groups? How would we even check if the solutions are correct? A intersect B equals C is one of the problems we want to solve. So we don't even know how to check the solutions once we've got them, never mind propagate them. So how do we go about solving this? How did Leon solve this? We rewrite our problem so the solution is all the permutations in the group. This only works if our problem only has a single solution, but for A intersect B equals C, where A and B are known, it does. So now each solution is an element of C. It's a single permutation. all of the solutions together form the intersection of A and B. And given a single permutation, we can check if it's in the intersection of A and B, because if it's in A and it's in B, well, then it's in the intersection of A and B. We, of course, still don't want to find all solutions to this problem. We only want to find enough solutions that we have a set of generators. And actually, I worked on this back in 2008. Myself and my wife, Karen Petrie, looked at this problem, and we found we could take if we had a permutation group on 1 to n, and we represented it as a constraint problem, we could split that constraint problem into order n squared pieces statically before we start search. For each of those n squared problems, we need to find only one solution. So either find the problem has no solutions or find one of the solutions. We don't care which one. And then if you put all those solutions together, we can guarantee you'll have a set of generators for the group. Now, this has got us much closer to where we want to be. It used to be that we would have to find a possibly exponential number of solutions. Now we only have to find n squared. So great, we've solved the problem, we've made it reasonable. In real life, we often want to solve problems where there are 1,000, 10,000 points that the group acts on. N squared is still too big. We kind of don't want to have to split a problem into 1,000,000 pieces and solve all of them. We definitely can't split a problem into 1,000,000,000 pieces and solve all of them. So this got us much closer than we were before, but still didn't solve it, and is not as good as what Leon had in fact done before us. I'm now going to just talk a little bit about complexity, and I'm not going to get deeply into complexity. This is a really interesting area in group theory. So usually, when we're doing constraint programming, we always talk about NP-complete problems. Many of the things we solve are NP-complete. The sort of standard definition of things like SAT and CP is that they're NP-complete. So one of the problems people want to solve in this area is graph isomorphism. So can you map a graph to itself? And this problem is famously not known to be NP-complete. Group intersection is known to be harder than graph isomorphism and is also not known to be NP-complete. These two problems, group intersection and graph isomorphism, can be solved in quasi-polynomial time. So this is faster than exponential time. Still not that fast in practice. The normalizer problem, which I mentioned, so this is you can think of this as the symmetries of a group, is, well, it's known that if you could solve this, you can solve group intersection, but it is still not known to be NP-complete. So we have this like nested thing. So there's NP-complete normal constraint problems. We don't know if that's harder than normalizer. We don't know if normalizer is harder than group intersection. We don't know if group intersection is harder than graph isomorphism. These might all be as hard as each other. Most people think graph isomorphism, when I ask people who are in the area, most people think graph isomorphism is easier than NP-complete, and we're not positive about these problems in between. However, we're not going to consider the quasi-polynomial algorithm. While it is an extremely interesting algorithm theoretically, it really isn't practically implementable. So, as I said, so there's no practical sub-exponential time algorithm for solving group problems. The most obvious way of finding an element of an intersection would be we could generate every element of the first thing and check if it's in the second thing. And we aren't going to beat that in the worst case. In the same way, in general, constraint solvers don't do better than their worst case behavior of just checking every assignment. What we're trying to do is solve a wide range of problems significantly faster. So, how do we go about splitting groups up, in particular, to try to get generators more efficiently? So, this is not a group theory course, but I'm going to give you a brief overview of some important group theory concepts. So imagine we have a permutation group, G and an integer I. The orbit of I is all the places I maps to by elements of the group. So this will be a set of integers, and this will be all the places you can get I to using elements of the group. The stabilizer of I is elements of the group, and it's the elements of the group which map I to itself. So remember, the orbit is integers, and the stabilizer is elements of the group. Let's give a concrete example which will hopefully make this easier. So if we consider the symmetries of a hexagon and we consider 1, the orbit of 1 is 1, 2, 3, 4, 5, 6, because if we just keep rotating, 1 will go everywhere. The stabilizer of 1 is the identity. It doesn't move 1 anywhere. And the reflection along the 1, 4 line. So swap 2 and 6 and 3 and 5, and that doesn't move 1 anywhere. So the orbit was size 6, and the stabilizer was size 2. You might think, oh, 6 times 2 is 12. That's interesting. In fact, this is generally true. The orbit stabilizer theorem, part of it is it says the size of a group is the size of the stabilizer of an element times the size of the orbit of an element. And we can go further than this. And so this bit's kind of important, and I'm going to give an example if you don't get it, so don't worry. Instead of just writing down the orbit of the group, the orbit of an element in the group, we are going to write down elements of the group that map our I to each of the places it can go. And then the group is equal to the stabilizer of I, the things that map I to itself, and these elements, this transversal that maps I to each of the places it can go. Let me talk about one. Let me give you an example. So here's the orbit of 1 again, 1, 2, 3, 4, 5, 6. And here is a transversal. So this is for each of these elements, map 1 to the thing we're interested in. So the first thing, like 1 maps to itself, we can just do that with the identity. 1 maps to 2, there's a permutation that does this. 1 maps to 3, 1 maps to 4, 1 maps to 5, 1 maps to 6. Let's pick one of these elements. So 4. So this maps 1 to 4. Remember that earlier we had the elements of the stabilizer of 1. So we had the 2 permutations that map 1 to itself. Here they are. Now I'm going to multiply these by that element that mapped 1 to 4. And this gives us the 2 elements of the group which map 1 to 4. So what this means is, if we want to get generators for all of a group, we can do it with divide and conquer. So first, we find one element that maps 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, if these exist. Then we find generators for 1 maps to itself. So this is our recursive step, and together those will give us generators for the whole group. And this was the basis which, way back, you remember I mentioned me and Karen had done something like this before, but we set this all up in advance and you can do it dynamically. So I've mentioned a whole bunch of problems on permutation groups which are hard, like intersection, normalizer, symmetries, which is the symmetries of a group. Let's consider some easy problems. And by easy, I mean can be solved definitely in a low order polynomial time. And most of these algorithms use something called a base and strong generating set. Now, I'm not going to have time to go into what a base and strong generating set is here, but I'm going to talk about the fundamental things they let you do. And 2 of the most important things you can do with permutation groups once you've built one of these base and strong generating sets is, given a permutation group G and lists of integers xi and yi, we can efficiently find an element of G that maps x1 to y1, x2 to y2 up to xn to yn, or if no such element exists, we can say no. And we can find a generating set and a base and strong generating set for G when we have fixed x1, x2 up to xn. And earlier I mentioned finding orbits and transversals. You don't need a base and strong generating set to get those. So we can find orbits, we can find the stabilizer of a point or a list of points, and in general we can say map x1 to xn to y1 to yn. Note that all these things must be lists. If you wanted the elements of G that map x1 to xn to themselves as a set, so could permute them around, that needs a backtrack search. It's as hard as group intersection. And similarly, we can't say map the xi to the yi in some order. We have to map x1 to y1 up to xn to yn. So now I'm going to go over how group theorists would traditionally think about doing intersections. assuming we know about base and strong generating sets. So we have our two permutation groups G and H. We pick an integer I such that G doesn't just map I to itself and H doesn't just map I to itself. If for every integer either G only maps it to itself or H only maps it to itself, then G intersect H can only contain the identity permutation, because for every number either G doesn't send it somewhere interesting or H doesn't send it somewhere interesting. So we're going to assume recursive step. We'll go and find the intersection of the stabilizer of I in G and the stabilizer of I in H. So we fix I in G, we fix I in H, which we can do in base and generating sets. Recursive call, assume we've done that, we've come back. Now we need to find a permutation for each place I can map to or prove they don't exist. Now we know that the places I can map to in G intersect H, so if I maps somewhere, if I maps to J in G intersect H, I must map to J in G and it must map to J in H. It is not the case that just because I maps to J in G and I maps to J in H, I will map to J in G intersect H, as we'll show. So for each of these J's, we find some G in the intersection such that I to the G equals J, or we prove that it doesn't exist. So how do we go about proving, how do we go about finding these permutations? Well, we try to solve a more complicated problem. We're going to say, find if there's a permutation which maps I1 to IN to J1 to Jn for some I and J. And I1 is going to be I and J1 is going to be J. So base and strong generating sets can tell us if G contains a permutation which maps I1 to IN to J1 to Jn, and whether H contains an element that maps I1 to IN to J1 to Jn. Of course, these permutations might be different. So just because J and H both contain such a permutation doesn't mean G intersect H does. But if G or H doesn't, then the intersection definitely can't. So basically, we proceed recursively. So if we want to know if there's something that maps I1 to IN to J1 to Jn, well, we pick some IN plus 1, which is different to everything that's come before. And then we look for permutation which maps I1, IN plus 1 to J1, Jn, Jn plus 1. This is classic recursive search. For each possible Jn plus 1, either we find such a permutation, either we find such permutations and they are equal, in which case we're done, and eventually we'll get to the point where G and H will only contain one permutation that maps the first list to the second list, or we'll find G and H. G or H does not contain such a permutation. And remember, in this part of the search, we only need one answer. Once we've found one element that maps I to J, then we're done. So what have we gained over just a brute force search? And in classic backtrack search style, as we're familiar in constraints, we can terminate early. So we build up permutations as a prefix, and we don't need to check every possible permutation. We can stop early. And the bit we gained group theory-wise is this idea of coset representatives. It requires more group theory than I can present here, but actually often once we've found a few generators in the group, we can prove that we can skip larger and larger pieces of the search by proving that they are symmetric to things we've seen before. So that's the basic techniques people used to use before Leon for doing group intersection. What did Leon add to this? Before I start talking about that, I'm going to take a very brief diversion and talk about graph isomorphism, because you'll remember Leon's paper said he was extending the ideas of McKay from graph isomorphism. So here's a graph. What I'm going to talk about here, the best presentation of this is in Practical Graph Isomorphism 2. A bunch of people have done work implying this in constraints. So here's one paper, I think this is one of the newer ones, a new filtering algorithm for the graph isomorphism problem, but there's been a series of these papers. I will say none of these things that have tried to embed this in CP have managed to be as fast as Naughty, and in particular, it is not uncommon for people to use Naughty on graphs of 100,000, 200,000 vertices, and typically those problems will not embed into a CP solver. And this is usually not a fault of the Propagator implementations, it's just most constraint solvers are not happy if you have 100,000 variables with 100,000 domain values. So how could we check this graph here? Let's imagine we want to find the automorphisms of this graph. So we want to find mappings that map this graph to itself. So consider the top two vertices slightly to the right. I'm going to colour the vertices and then describe what the colouring is telling you. So those two yellow vertices, they have two neighbours, and they're the only vertices which have two neighbours. So in any mapping of this graph to itself, those two vertices have to map to themselves. They can either stay where they are or they can swap around, but the yellow have to map to yellow. Similarly, the blue vertices have three neighbours. So all the blue vertices have to map as a set. And then finally, we have the red vertices, and those vertices have four neighbours. So they have to map together as a set. So this is the first step of McKay's algorithm, but we can go further than this. So consider the red vertices. So some of these red vertices are adjacent to yellow vertices. And because the yellow vertices have to map to themselves, red vertices which are adjacent to yellow vertices also have to map to themselves. And similarly, some red vertices are adjacent to blue vertices, and a red vertex which is adjacent to a blue vertex has to map to itself. And finally, one red vertex is adjacent to two blue vertices, and that vertex has to map to another red vertex which has two blue neighbours, except it's the only thing with two blue neighbours. So now I have coloured the red vertex which had two neighbours which were blue. I've coloured it green, and in general we've separated the colour classes again. So now we've actually got quite a long way towards solving our problem. But eventually we're going to get stuck. So how do we progress? As ever in constraints, we branch. So we can branch now. We could do a little bit more colouring, but I've got bored. So pick this vertex here. I've now highlighted it in brown. This vertex is either going to map to itself or it's going to map to the other yellow vertex. And if I coloured this, then I can further colour the vertices using now this new brown colour. Consider things that map to brown. And as I work my way through, it's colouring the things down the side. And eventually every vertex has its own colour. So let me now consider a second copy of the graph where I coloured the other vertex brown. And as I colour the graphs in sequence, we can see the colours changing, and now I'm at the point where in both graphs all vertices have a different colour, and now I can just read off the permutation where I made those two brown vertices, the thing that mapped the first brown vertex to the second brown vertex, by mapping colour to colour. So this is the fundamentals of graph isomorphism. So you use this colouring technique to identify different vertex classes, and then when you branch you make copies, and you know colours from the first one map to colours in the second one. Here's another graph. So this one, every vertex has three neighbours. So initially we can do nothing. There are colouring techniques which would let you do colouring on this, but let's consider this most basic one. But let's say, how do I map this blue vertex to this blue vertex? So how do I map the first vertex to the second vertex? Well, its neighbours will have to map to its neighbours. So now the three blue vertices will have to map to the three blue vertices. And then I do another stage of colouring. And the red vertices on the left will have to map to the red vertices on the right. Except there's two red vertices on the left and there's three red vertices on the right. So actually, we can't map the graph on the left to the graph on the right, which means those two vertices I selected, there is not a way of mapping the first one to the second one. So this is another important thing that makes this differ from the way we might think of a traditional constraint problem. We kind of have two copies of the problem that we run in parallel, and we look to see if they ever deviate from each other. And if they ever deviate from each other, we know that there isn't something that maps the first one to the second one. And we have these properties where if there is something that maps the left to the right, the colours will keep with the same number of colours, and things on the left will map to things on the right. So this is what Leon generalized. So he invented this concept of what he called a refiner. These are very similar in flavour to what in constraint programming we would call a propagator. So we represent the current colours in the graph as a function from the vertices to colours, and then the symmetries permute the vertices of the graph, so they swap the colours around. And then given two coloured graphs, or two states, we say the current set of permutations we're considering are the things that map the left graph to the right graph. This is what this is saying. The left and right graph look the same, then this will be a group. And if the left and right graph, if they're not obviously the same, then this will either be a coset or it will be empty. This is very different to how a CP or a SAT solver would store things, where we'd have a list of possible domain values for each vertex, whereas here each vertex just has a colour. This does have several advantages. It only requires order number of vertices memory. So you can store these partitions using order size of V memory. And it's easy to represent that two vertices have the same colour, so they form a class that will map to themselves, or we know they have different classes without yet having to kind of fix the final colour choice. So we haven't yet decided where the vertices are mapping, we just have this concept of equivalent and inequivalent vertices. And typically, while I didn't go into details here, there'll usually be a well-formed way of defining the colours. So we might have a colour that represents like 2 neighbours, or 3 neighbours, or 4 neighbours, so we can tell the difference as the algorithm progresses. So the things with 2 neighbours have to map to the things with 2 neighbours, and so we keep the colours consistent. And so then a refiner is just something that takes 2 of these coloured graphs. So here we have 2 states, so our states are these omega to C, so vertices to colours and vertices to colours. And so what this statement in the middle is saying, it's a bit complicated, but what it's saying is we have our solution, the refiner we're currently implementing. So say we're implementing a refiner for some coset PG or some group G, and it's saying the permutations which currently map the first set of colours to the second set of colours, you're allowed to do recolouring such that the solutions which are currently represented by those colours are still represented by these colours. So this is one of those things. It's similarly in Constraint, it's difficult to explain. You're not allowed to lose solutions. You can recolour the graphs, you can recolour the vertices, but you are not allowed to lose solutions. So the idea is you split colour classes, but only when you're sure you're not losing isomorphisms of the graph. So then in search, we have these refiners, and they take the colour classes and they replace them with new colour classes, where we simplify, keep splitting classes as we go down. So what Leon's breakthrough was to realise that this colouring we're doing in graphs, which is what I've done here, we can do this for any constraint. So previously the constraint was that the graph maps to itself, but we can do this for is in group, stabilizes set, is a normalizer. And so we invented effectively a constraint solver which had lots of different constraints by saying I can write colouring functions for all of these different properties, and I can use them all at the same time. And now, instead of using the approximation of, well, we just take the orbit in alpha of G and the orbit in alpha of H. Remember, way back when we were searching, we would take a point and we'd take where it maps to in G and where it maps to in H. We can use the orbit approximation returned by the refiner. So we take the refiner for G, the refiner for H. We let them find an approximation for the orbit of alpha, and the orbit of alpha will be things with the same colour as alpha. That's places alpha can map to. So now I'm going to look at taking 1 and fixing it in G and taking its orbits. That's at the top, 1, 2, 3, 4, 7, 5, 8, 6, 9, and then also fix 1 in H and take its orbits. Don't worry about what the groups actually are here. I'm just interested in what the orbits are. Then I'm going to imagine these as colouring. So the idea is you label the things in the first orbit of G some colour, the things in the second orbit of G some colour, the things in the third orbit of G some colour. And similarly, you have a colour for each of the orbits of H. And the colours for the orbits of G and H are different. So we would say 1, so this is the first thing in this list. So 1 is in orbit 1 in G and orbit 1 in H. 2 is in orbit 2 in G and orbit 2 in H. 3 is in orbit 2 in G and orbit 3 in H. So this means we know that 2 can't map to 3 in this when we fixed 1. When we fixed 1, 2 can't map to 3. And in fact, in general, if we go down this list, 1, 2, 3, 6, 4, 7, and 8 are all fixed. So nearly everything has been fixed by just taking the orbits. So there's still and also we can take the orbits where we fix 1 and the orbits where we fix 2. Here they are. So in the first one, we look at where 1 map, we look at the orbit for 1, the orbit for 2, the orbit for 3, etc. In the second one, we look at the orbit of 1, the orbit of 2, the orbit of 3, and we can read off where things. So remember before when we had a graph on the left and a graph on the right, they were different colours. Now we've got the orbits of G1 and H1 and the orbits of G2 and H2. And so, for example, in G1 and H1, 1, its colour in inverted commas is the pair 1, 1. When we fix 2 in G and 2 in H, then 1, 1 is the colour of 2, so 1 maps to 2. So the thing that was 1, 1 in the first maps to the thing that was 1, 1 in the second. Now, we know at this point that we fixed 1 in the first and we fixed 2 in the second, so really we better have 1 maps to 2, because we fixed 1 and we fixed 2, but we can read off where almost everything else maps to by looking at this in inverted commas colouring, and the only thing we don't know is we know the pair 5, 9 maps to the pair 4, 9 in some order. So if there is a permutation in G intersect H which maps 1 to 2, it maps 2 to 1, 3 to 3, 7 to 8, 4 to 5, 6 to 6, 8 to 7, and the pair 5, 9 maps to the pair 4, 9 in some order. But we don't know what that order is. So we could do a recursive search to find it. I'm not going to. So we can similarly consider, is there an element that maps 1 to 9 by considering the orbits when we fix 1, the orbits when we fix 9. And once again, we look at the colours of each of the vertices in the first case and the colours of each of the vertices in the second case. And this time we can notice, so when 1 maps to 1, only one thing is coloured 2, 2. So only one thing is in the second orbit of G and the second orbit of H. Whereas when we fix 9, there are 2 things which are in the orbit of both the second orbit of G and the second orbit of H. So there's 2, 2. So similarly, when the number of occurrences of each colour got different in the graphs, we could stop. Here, when the number of colours get different, we can stop as well. Just in case you are curious, you might think, how do you know what the first and second and third and fourth orbit of the groups are? How do you order the orbits? The answer is, there are a bunch of technical lemmas, and you'll just have to believe me or go and read the associated papers. There is a way of ordering the orbits in a consistent manner, and I apologise for not going into details. So we have these general concepts of refiners that do these colour classes, and just like with propagators, if I take a refiner for some constraint C and a refiner for another constraint D, what this is saying is I can apply the refiner for C and then the refiner for D, and I get a refiner for C intersect D. So just like in a normal constraint solver, I'm allowed to take a whole bunch of constraints, put refiners in for all of them that do this colouring. Lots of things can do colourings in different ways. I can even have multiple refiners for a single constraint. So, and Leon does discuss this. He sometimes has like an easy refiner and a more complicated refiner, the same way we might have implied constraints or 2 refiners for the same constraint. So in particular, if at some point, so this line here, iso equals no, if at some point we notice that we're colouring our 2 sets of vertices and we notice the first one can't map to the second one because the number of colours, for some colour, there is more of that colour in the first graph than the second graph, then we know the problem doesn't have a solution and we can backtrack. So just, I don't want to go into full details. So the refiner for group regenerators, the refiner I've just been discussing, we take the vertices where we know the colours are fixed, where there's only a single vertex with that colour, and we fix those in the group. And we always know we can do that because, as we mentioned earlier, based on strong generating sets, if we have a list of fixed points, we can take those fixed points and fix each of them in the group and get things for the resulting group. And then we have to order the orbits in an annoying technical way I don't want to get into. Similarly, a common thing for people to want to do in groups is to say which elements of a given group map some set to another set. And that's easy with colouring vertices. We just colour the things in the set we care about one colour and the things which aren't another colour. So, big picture, stepping back for a minute, what did Leon produce? So in his extremely dense paper, so I want to say this paper he wrote is incredibly dense. It is very difficult to read and I wouldn't recommend it. If you really want to understand it, do feel free to email me. I have an extended version of slides with even more group theory and to help you understand. We also have my own paper which extends this work, which I would recommend you try and read first before you read Leon's. But he did an astonishing amount of things. So he had this idea of this representation where for permutations where you have two partitions and you map the first to the second one, this colouring thing. Dynamically finding the generating set of a group. He invented independently this concept of refiners, which is like propagators, and he implemented them for 6 different constraints. And then then you have to do all the standard things. You have the constraint solver, you have the concept of a queue, you need to run the refiners to fixed points. He talks about variable and value orderings. He has this really interesting thing where some of the refiners can, as they're running, suggest possible variables and value orderings based on what they think would be good. He does some symmetry breaking independently from dynamically finding the generating set. It really is an astonishing amount of work in this little bubble by itself, which had broadly not had much work done to it since. So there is a few things which build on it before myself and my co-author started looking at this. In particular, there was someone called Heiko Tyson who did better refiners for normalizers. So, how did we build on this? So, turns out we wrote 4 solvers. So first of all, we tried to do a fairly simple implementation of Leon's framework. Simple and a direct implementation of his framework, but efficient. And so we did this, and we used this to make some small extensions. This is called Ferret. The name doesn't really mean anything. We just like the idea of ferreting to search out solutions. And you can find this at the URL listed here. Then, after we did this, we realized one of the problems with this, it was written in C++, it was high performance, it was very difficult to read. So we did a purposefully clean and very simple implementation in a package we called Backtrack Kit. So the idea is this is for group theorists to help them understand how to build backtracking algorithms. It is extremely inefficient, like 1,000 times, 10,000 times slower than Ferret. It is intended as a teaching aid. Then we looked at this work and we thought, how can we take the knowledge we have from CP and generalize and extend it? And this was the package Graph Backtracking. So this produced smaller searches than Backtrack Kit and was more general. It could solve more types of problems. So we generalized it to solve what are called canonicalizing problems, where you want to, given a graph, find a canonical image of the graph. So the idea is if graph A maps to graph B, A and B will have the same canonical image. And it solved a much wider range of problems. And for many problems, it was orders of magnitude smaller searches. But it was still designed to be easy to understand and very inefficient. We worried purely about the sizes of the search, not about how fast the searches ran. And then finally, we re-implemented the whole thing in the Rust programming language. We called this Vol, kind of inspired by Ferret. So this aims to be a highly efficient generalized solver. And this is our current area of direction. So what did we take from constraint programming? So first of all, while there was some work on variable and value orderings in Leon's paper, we could do much better. We could think about how you order the propagators or refiners. We added restarts, we added some parallelization, we added very basic learning so far. We did a much more testing and benchmarking. This is an often underrated thing, I think, in other areas. Backtrack searches, in my opinion, are notoriously difficult to test for correctness. You have a whole bag of propagators. Often bugs will only be revealed in those propagators when multiple propagators are running in the search. There have been several papers in this area. I was involved in a paper myself. There's been other work, but we had a big testing framework that would solve lots of different problems. It helped there were other implementations of the framework. There was a pre-existing implementation. While it was much slower, we compared against it under the assumption we hopefully wouldn't produce the same bugs. And also there were some other lessons. propagators, refiners are very important. If you look in CP, there are many, many more papers on propagators than on general solver design. Most people are not building new solvers, they're building new propagators to go in existing solvers. And so we put a lot of work into writing more and better refiners. First, we introduced a concept of perfect, which is similar to the concept of whether a propagator is GAC or generalized arc consistent. This is like the best a propagator can be. Because we're working on this idea of representing things as permutations, it's not quite the same as generalized arc consistency because we don't have arcs. Turns out a bunch of the refiners Leon had described were already as good as they could possibly be in terms of how much refining they did, but there were other cases where we could produce better refiners or propagators. In some cases, we could prove the best possible propagator would itself be graph isomorphism complete or MP complete, so we couldn't hope to use it in practice, but we could get much closer to it. As an example of a better refiner we came up with, let's consider the refiner for group given by list of generators. So the refiner I described earlier is we take the orbits of the group, and in general what we do is we take points which are known to be fixed, so this would be vertices where there's only one vertex with that colour, fix all those points, which is a thing we can do based on strong generating set, and then take the orbits of the resulting group. But what can we do if there are no fixed points? So there might be like 3 blue vertices and 7 yellow vertices, and at the moment we're not making use of that information. This would be like a propagator in CP, where the propagator only considered the fixed points, it didn't consider the domains of variables. Now, of course, what we'd like to do would be to say, take the group, fix the blue vertices and the green vertices and the yellow vertices, and then take the orbits of the result. However, that problem is known as the ordered partition stabilizer, and it is another one of these problems we have to use backtrack search to solve. So we can't use that information. But even if we fix the points, can we do better than just taking the orbits of the resulting group? Because a group has lots of structure. What richer information could we use? So we went around looking for information which is relatively cheap to calculate, but lets us generate more information. So let's assume that we have a group again. We have 2 points alpha and beta, 2 integers. Then the orbital graph of alpha and beta, these two numbers, it's a graph on the integers, our vertex at omega. And basically we take all the images of the pair alpha beta under the group, and this is the edges of the graph. So this can be thought of, so orbits is you take one number and you take all of its images under the group. Orbital graphs are you take 2 points and you take all images of that pair of points and you get a graph. And it turns out orbital graphs are well studied, they can be generated efficiently, more efficiently than just taking a pair of things and finding all its images under the group. And the most important thing is, if we take all of these orbital graphs and we take their automorphism groups, so imagine we're doing graph automorphism, we can use these as extra refiners. And I wrote a paper with Marcus Pfeiffer and Rebecca Waldecker where we use this information. So I mentioned his name earlier. There was a previous person called Heiko Tyson who had looked at a similar technique for finding the normalizers, this symmetry group of groups. In a similar way, but we looked at it just for things like group intersection. So to give you a feeling for how this works, so imagine we've made this. So if we had, so this is something like the symmetries of a septagon instead of a hectagon, and if we make an orbital graph with 1, 2, then we get edges that go all the way around in a circle. So we take the image, all the images of that edge under rotation, and we get all these edges. Fair enough. Now imagine in our partition we have coloured 1 and 3. So we imagine some other refiner has distinguished 1, 3 from 2, 4, 5, 6, 7. Now if we use the normal refiner for groups, there's no fixed points, so we couldn't do anything. The symmetries of this thing, 1 maps everywhere, so the orbit of 1 is everything. But now we're allowed to use build this graph and do equitable partitioning, the colouring of graphs, and it fixes all the vertices. So this is an example of how we can do better at refining by making use of extra information, the type of thing we do in constraint programming all the time. We think of better representations and we use those to build better propagators. And another thing we think a lot about in constraint programming is how we represent the variables themselves. So there's been a move in recent years. We can consider sets and multisets and functions directly instead of breaking everything down into integers. And if we break them all down into integers or booleans, we think of different ways of representing them. So one important class of groups is what we call the transitive groups. So these are groups where you can map every point to every other point. And as we said earlier, the problem at the start of search, if you can map every point to every other point, you can't do any coloring at the start. So if we're trying to intersect a bunch of transitive groups, while their intersection might be small or even just the identity permutation, you can't do any coloring at the start. Sorry if this doesn't quite make enough sense, but just think there are hard problems. And so what we do is, instead of just storing colorings in our solver, we allow more complicated structures. So there's these things called block structures, but in this case we consider graphs and hypergraphs. So the idea now is, instead of refiners returning a coloring, they can return a graph. So before we would build a graph and then we'd do the coloring. What is the advantage of letting refiners return a graph instead of just a coloring? So I'll give an example. So imagine we had a refiner that made this graph internally, and we can't do any coloring because everything has two neighbors. A different refiner makes this blue graph. And once again, if you just have the blue graph, you can't do anything. Everything has two neighbors. So if these two refiners both build a graph separately and try to do coloring, they won't be able to accomplish anything. But if we take both graphs and we push them into the solver, then now you can look at both of these graphs simultaneously and you can distinguish the vertices. So you can say things like, you can see 5 and 6 are different, and you can do coloring where you use the multicolored edges, and you can distinguish the vertices of this graph. So actually, we can color all of these vertices and distinguish all the different colors. So this raises some interesting lessons for CP, I think. So one thing is how variables are represented is fundamental. And one thing I found interesting about all of this coloring business is it really opened my eyes up to new ways of representing the state of problems. In constraint programming, we tend to very much have a finite domain image. Not everybody, there are various solvers that do different things, but in general, we do finite domain. Classically, if we map things to SAT, it's all Booleans. And there are things where you can do interesting things like this coloring, which does let you solve much bigger problems because the representation is order n, where n is the number of points the group works on. It is reasonable and possible to work on groups on 100,000 points, 500,000 points, whereas if you represented it in a traditional constraint solver, it wouldn't work. Also, if we make the things that refiners, propagators are allowed to return, so we added the concept that refiners could return graphs instead of just a coloring, this allowed exponential search reduction. It also made the refiners much simpler. Now, almost every refiner, it builds a graph, it returns it almost immediately. Whereas before, refiners were doing lots of common work. They would build the graph and then every refiner was doing the coloring themselves. Or if they weren't building the graph, they were doing the same kind of reasoning as if they had built a graph. Also, and this is, I will be fair, more a discussion for mathematicians than for many practical problems. It is very common in mathematics that problems have structure and people want the entire structure, whether it be a group, a semigroup, a monoid, vector space. There's many different structures that come up. You need to build this structure. Typically, you have to build it in pieces. You can't just write a problem that finds the whole solution in one go. And a group is just one of dozens of types of algebraic structures people study. So we've concentrated on groups in our system. There are many similar structures and you could look at ways of representing them in problems. If you're curious, we did consider trying to extend our existing solver to do things like semigroups, and it's very difficult. It doesn't just immediately generalize in an obvious way. There's really interesting technical reasons that what we've done really works well for groups and doesn't work for most of the other things, which I would be happy to discuss. This is the end of the main theory part of my talk. I am now going to demonstrate the system we built in action, just so you can see it running. The Vol group theory solver is distributed as a package for the GAP programming language. GAP is a programming language designed for group theory. The reason we do this is twofold. Firstly, many group theorists use GAP, so it provides them easy access to the package in a language they're already familiar with. And secondly, GAP implements many algorithms which Vol itself uses, in particular the base and strong generating set I discussed earlier. After you've installed GAP, you'll need to install our packages, which are distributed from peel.github.io. The package you really want is Vol, but in order to use Vol, you'll have to install both graph backtracking and backtrack kit. Each of these comes as a tar.gz file. After you've installed GAP, you install it into the pkg directory of GAP. If you need more help doing this, please do get in touch. Once you've got GAP installed, got all the packages installed and got it loaded, you'll find yourself at a prompt like this that says GAP. As I say, if you need any help, do feel free to get in touch. This demonstration command I'm running just lets me step through a series of commands from a file without having to type them all in. So GAP is a complete programming language. Here we can see I'm assigning P the value of a permutation. Permutations in cycle notation are built into the language. GAP uses :equals for assignment, unlike the more traditional equals. The GAP website has a full tutorial for the language if you're interested. So we can define a couple of permutations like this. We can make a group out of these two permutations. This is the group of hexagon symmetries we were talking about earlier. We can ask for the size of the group. It's 12. We can ask for the orbit of 1 in this group. Here it is. We can ask for a permutation which maps 1 to 4 within G, and here's one of them. This is the reflection we saw earlier. So, what else can we do? We can make a second group. So here, this is declaring a group from one permutation, the permutation that moves 1 to 3 to 5 to 1, and 2 to 4 to 6 to 1. Now, I'm going to load the Vol package. The false at the end just stops it printing the copyright information of the package, which takes quite a lot of the screen. You can skip that. So the fundamental idea behind Vol is there is a series of functions which start Vol find. So let me show a command and then explain it. So volfind.group is finding a group. So we're saying the solution we're looking for is a group. It's going to give us a set of generators for that group. All of the constraints begin volcon. So this is saying run the Vol solver to find a group, and we want the solution to be in group G and also in group H. And we just give a list of constraints and here's the solution. Turns out that the intersection of G and H, so if you think about it, the group which is things which are in G and also things which are in H is G intersect H, turns out to be H. You can see this because the generator is the same as the generator we had for H earlier. We can, if it's all we care about, just ask for a single permutation from the group. So rep means a single representative. Now, in the case of intersecting two groups, it could have given us the identity, because the intersection of groups will always be the identity. Remember, we can operate on groups and cosets. Intersecting cosets isn't trivial, and they might not have a member in them. And also, there's no requirement it finds the identity element. It doesn't in this case. Now, at the moment, we've only considered one group. So in group should perhaps better be described as in a group given by a list of generators. But we can describe groups in other ways. For example, here we say we want something in the group G, and the way this should be read is volcon.stabilize, so stabilize 135 as a set. So in GAP, the language is a little strange. On sets means treat the argument as a set. So it's saying treat 135 as a set. So find the elements of G which map 135 to themselves. And it turns out there is a group that does that. and its generators are given here. So one thing I'm just going to mention quickly before I move on, quite a lot of things in GAP operate on infinite permutations. GAP acts as if permutations fix all points up to infinity. So the P1, which cycles 1 to 6, if we ask GAP, it would tell us that it cycles 1 to 6 and fixes all other integers to infinity. So sometimes we have to explicitly give a largest move point, which means we want permutations and this is the largest thing we want them to move. So we can say, this is a stupid problem. We can say, find the group where the largest move point is 4. So you can do anything you like 1 to 4, and these generators generate all the permutations that cycle 1 to 4. The reason that I mention this is when we look at directed graphs. So here we have a directed graph, and the way to read this is it's a list, and the ith element of the list tells you what I is connected to. So this tells us there's an edge from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 back to 1 again. And this graph is treated as if it had the infinite number of vertices going up through the natural numbers, but those vertices all just have no edges. So if we asked for the things that map this graph to itself, we would get an error message, and it would say, I can't give you an infinite group. The group has to be finite, and this group wouldn't be finite because it could map all the vertices from 7 upwards to themselves. So if we want to ask for the things that map this graph to itself, we have to explicitly say, stabilize this graph. So on digraphs is the word that means map graphs to themselves. And then we say, largest move point, only we care about 6. And it turns out this graph, it is the graph, its automorphism group is just 1, 2, 3, 4, 5, 6, just cycling 1, 2, 3, 4, 5, 6 round. The digraph, the di means the graph is directed. So if you've ever heard of naughty, this is exactly what naughty does. Solves this problem. Now, naughty does still do it quite a lot faster than vol at the moment. Vol isn't bad, but it's not as good as naughty. We hope to close the gap over time. But I can make a second graph, and I can say, give me a permutation. So this is find a single element. And now we're saying vol_transport. So now we're, instead of saying map D to itself, we're saying map D to D2. So this is saying find a permutation that maps D to D2. And go and get the largest move point. And just to say, we can glue all the various constraints we've seen together. So we can say, I want to, in this group, I want to stabilize 1, 3, 5. I also want to stabilize 1, 2. And it turns out this notation here, so this is telling us the solution is the group, which only contains the identity element. So there are no interesting permutations that satisfy all 3 of these constraints. Just to say, we can do bigger graphs. I can make the graph on a cycle graph on 10,000 vertices, and I can ask vol to find the automorphisms of that. And turns out there's one thing, it's the cycle on 10,000 points. So we can solve big problems. We'd like to be able to solve even bigger problems. So far the things we've seen, the graph things are things which naughty can do, and the group things are things which Leon's code could do, although vol often does them faster because it has better refiners. But what can we do that we couldn't do before? So to begin, we'll just start with something else that we could do, something naughty can do. We can ask naughty for a canonical permutation. And this is a subtle thing. The idea is, if I give you 2 graphs, D and D2, let me run D and D2. It gives you a so the canonical element, it is a permutation. So symmetric group 6, sorry, lots of things going on here. Symmetric group 6 is all the permutations on 1 to 6. And what is happening here is we're saying give us a permutation from that first group, symmetric group 6, where if D and D2 can be mapped to each other, then the permutation C1, the permutation we got when we applied D, and C2, the permutation we got when we applied D2, the permutation C1 applied to D and the permutation C2 applied to D2 will get you the same graph. So the idea is this gives us a permutation that will map all graph to a canonical version of that graph. So I can say apply, so on digraphs, this is how we apply a permutation. So to the digraph D, apply C1.canonical. C1 returns a record. The canonical is the canonicalizing permutation, and we can apply C2.canonical to D2. And so this is telling us that we can map D and D2 to the same graph. And if what we wanted to do was map D to D2, then starting from D, we could first apply C1.canonical, and then we could apply the inverse of C2.canonical, and that would get us to D2. So the way to think of this, it's a way of checking if you can get from one graph to another by moving them to a canonical or standard version of the graph. Naughty does this. This is one of the famous things that Naughty does. However, what Naughty cannot do is let you give a different group. So Naughty will always give you the canonical version of a graph where you can relabel the vertices under any group. We can give an extra group as that first argument. So we can say find the canonical image of this graph under this group. And so now what this will tell us is if there's a way of mapping D to D2 within the group G. There are lots of applications of this in group theory. I'm afraid I can't give you good examples of applications right now. You're just going to have to believe me. And now if I ask for apply C1.canonical to D and C2.canonical to D2, it's false. So there is not a permutation which maps D to D2 in G, this tells us. If you're wondering what the difference is between rep, so rep gives you a function, gives you a permutation that maps directly from D to D2, and canonical does this thing where it maps you to a standard image. So rep is generally faster. If you only have two graphs, D and D2, just ask for a representative element that maps D to D2 within a group G. The reason we use canonical is if you had, say, 10,000 graphs and you wanted to put them into equivalence classes, if you used rep, you'd have to apply it to every pair, whereas canonical, you can get the canonical image of every graph and then just sort the canonical images afterwards. We can also take the canonical image of any object. So here we're saying find the canonical image, we'll go back to the symmetric group again, of the pair D, then D2. So this is, once again, Naughty can take the canonical image of a graph, we can take the canonical image of a list of graphs or a set of graphs or a graph and a group. Because everything's compositional, it's constraints. You can put any of the refiners in this position. One of the many things I don't have time to talk about, we use the same refiners for both group and rep and canonical. The search function changes, the refiners stay the same. So as soon as you've written a refiner for finding group intersection, you instantly get rep and you get canonical for free. So we can ask for the canonicalization of the list D, D2, and then the list D2D. So this would tell us if there's a permutation that maps D2, D2, and also maps D2 to D. And indeed, our results, turns out, do that. So C1.canonical applied to D and C2.canonical applied to D2 gives the same graph, and D2 applied to C1 canonical and D2 applied to D gives us the same. So this tells us that there is a permutation which maps the pair DD2 to the pair D2D. There is lots of other stuff you can do here. If you enjoy group theory, you're very welcome to have a play. If you have any questions, do feel free to email me. This is the end of my talk. Thank you very much. I hope you have enjoyed this and understood a reasonable amount of it. As I've said, I find this weird alternative world which has existed for nearly 30 years now in group theory that's almost but not quite constraint programming really interesting, and it really has been interesting for me to try to combine the knowledge I had from constraint programming and the knowledge I've picked up in group theory to produce this new system, which group theorists are already using to solve interesting problems that they find in the sort of boundaries of mathematics. Thank you very much.